Here we have a 2-for-1 theorem. 2 for the price of 1. So pause, copy, pause, copy. Oh boy, pause, copy. Okie dokie. So 2 for 1. We want to find the area of this parallelogram and the area of this parallelepiped. Say that 3 times fast. Parallelepiped, parallelepiped, parallelepiped. So parallelepiped is a kind of a 3-dimensional parallelogram. If I were to think of this point here, the corresponding vector would be a1 plus a2 plus a3. Anyhow, so in 2x2 case, we're finding an area. And what you do is you just find the absolute value of a determinant. Determinant of this matrix. So you'd go area is equal to the absolute value of a determinant. So it's a bit weird because you got the shortcomings of the notation are on display here. 1 minus 6. Because, well, you want that absolute value, right? Because you want, well, you can see why it's necessary. You can't have a negative area. And for parallelepipeds, we'll have to do a 3x3 determinant. So anyhow, let's do an example to demonstrate. So pause, copy. So we have these vertices. Let's go ahead and draw them now. Look at my numbers here and see what my scale should be. Okay. Looks like I'm going to have to leave some room in the top right. So 6. So I'll put 4 here. 2 goes in the middle. And 6 will go here-ish. And then where am I? Right, 4. I'll put a 4 here. 2, and then my 2. Beep, beep, beep. Beep. Okay, let's start plotting some of these vertices. So we're going to have a problem here because none of these vertices are the origin. So what we're going to have to do is shift our parallelepiped. This is really, something's gone wrong. 6, 4. -2, -2, 0. Oh, this one is in the wrong place. Oh, that's not good. Well, you know what? I can't delete that. Let's scratch it out. It should be up here, 0, 3. Okay, that is a parallelogram. The 4 remaining vertices. So it's not, what I want is at least one of the vertices to be at the origin. So what I'm going to do is I'm going to shift this one to the origin. So I'm going to add something to all these vertices. I'm doing a vector addition essentially. So I want to move this one to the origin. So I should add 2, 2. So what do I get? I get 0, 0. 2, 5. 6, 1. And 8, 6. Okay, so what does that give me? It gives me a dot here, 2, 5 is, where's that? About here. And then the 6, 1 would be about here. And then the 8, 6 would be roughly 8, and then up here. So I get this parallelogram like this. So this should be, I'll let this be the first column of my matrix, and I'll let this be the second column. So A is equal to 2, 5 is my first column. Second column is 6, 1, 6, 1. So area is equal to the absolute value of the determinant of A, which is 2 minus 30, in absolute value 28. Okay, to recap, in blue, I had this parallelogram that was not where I wanted it to be. If I want to use the theorem, I need to have one of the vertices at the origin. So what I did was I shifted everything by the vector 2, 2. So thus moving this vertex to the origin. And then I was able to use the theorem, and I got 28. Okay, we can actually go further with this idea. Let's say you have a linear transformation. And let's say you have some blob. We'll call it S. And let's say you apply a linear transformation and you get some other blob, which we'll call T of S. So you have a transformation of a blob. So what do I mean there? I mean you have this blob consisting of vectors here, right? Well, you think of them as points, but typically we think of points as vectors in this course. And you transform all of those vectors using your given transformation T. You get a new blob. And we want to say, what's the connection between the area of S and the area of the transformed S? And this is the content of Theorem 10. Theorem 10 says, the area of T of S is equal to the absolute value of the determinant of A times area of S. So where A is the standard matrix of T. So a very nice little formula here. So if, sorry, we'll say in R3, this works as well. You have volume of T of S is equal to absolute value determined of A times the volume of S. Okay, so the same idea actually works there. I'm not going to attempt to draw a three-dimensional blob, though. Okay, so it gives a nice formula, which we will now attempt to use. So let S equal a parallelogram determined by, give two vectors here, -2, 5, and -2, 3, and let T of x1, x2 be a linear transformation given here. And we want to find the area of T of S. So we're going to use this formula up here. So we're going to need the area of S to begin with. Okay. Of T of S is absolute value determinant of A times the area of S. So what is the matrix A here? Well, I can read it from the given T. It's going to be 6 minus 2 minus 3, 2. Okay, so I get that. Times the area of S. S is determined by these vectors, so I just throw those into a matrix. Okay, do not forget your absolute value on the outside. So there we go. What do we get? 12 minus 6 dot -6 plus 10, which is 6 times 4 is 24. Okie donkey. Okie donkey, okie donkey, okie donkey, okie donkey, okie donkey.